Imagine you're a counterfeiter and your objective is to sneak some fake money past the police. If you're the police, your aim is to accurately distinguish between this fake money and real money. Now, due to this intense scrutiny by the police, the counterfeiter will end up producing fake money that very closely resembles the real money, with the end goal of making them indistinguishable from one another. In other words, the counterfeiter has to learn a generative model of real money. Now, believe it or not, such a simple idea has seen very successful application in the domain of machine learning, where it can be used to generate high-quality synthetic examples of everything from images to speech. This is the fundamental idea of the Generative Adversarial Network, or GAN for short. At its heart is a unique adversarial learning framework that pits a generative model, which is our counterfeiter, against a discriminator, which is our police. The discriminator learns to classify real from generated samples, and the generator tries to trick it. By this competitive process, the generator can eventually create samples that are realistic, giving us a working generative model. So in this video, we're going to explain how this works. We're first going to motivate the GAN by introducing the general problem of generative modeling, and then explore how the GAN addresses this problem. So what exactly is generative modeling? Well, let's assume that we have some input data variable x, and this could represent anything, for example, an image. Now imagine that we want to train a model that captures some target distribution in the data space, and this could correspond to any intended category, like cats. So in this example, a successful generative model would be able to generate novel images of cats just by sampling from this learned distribution, which we call p-cats, and it may also be able to perform things like anomaly detection when faced with images of things other than cats. Now, more formally, let's imagine that we have some dataset D, which is just a collection of points in our data space. Now, we imagine that these points in our data space have been sampled from some underlying data distribution P star of x. So P star of x here is essentially our ground truth generative procedure, which gave rise to the samples in our dataset in the first place. Now, the problem is this procedure remains unknown to us. So the best that we can do is try to approximate it by using some model p theta, where theta are the model parameters. So the basic goal of generative modeling is to optimize theta such that our model distribution aligns as closely as possible to our target distribution p star, and to enable sufficient flexibility in our generative model, we'd usually represent it using some kind of deep neural network. On the face of it, this problem looks pretty simple. We can just spin up some arbitrarily powerful neural network and treat the neural network output as the probability of the input x. However, it turns out that the situation is a bit more complicated, since if we want our neural network output to represent an actual probability distribution, then we'll need it to satisfy two additional criteria. First, the inputs all need to be non-negative, which is a condition of any probability density. Now, we can easily solve this by just applying some kind of positively valued function phi, which could be something like an exponential, on our neural network output. However, the second condition is a bit trickier, and it basically says that our function needs to be normalized, such that its integral over the entire space is equal to 1. And again, this just stems from the definition of probability. So, if this integral happens to equal something else, which we'll call z, then we'll have to normalize our output through division by z. Now, the problem is that this integral is typically intractable to compute, meaning that in general it does not have an analytical form, and it'll also be very expensive to estimate by sampling if x has a high dimension. Now, not being able to compute the normalization constant is a big problem, because then if we optimize theta to directly increase the numerator of our output, we can't actually be sure that we're increasing p of x overall, since we may be increasing z by an even greater amount without knowing. So this issue of intractable normalization constants is one of the central problems of generative modeling. Now, GANs sidestep this problem by essentially just reframing it. Now we're not really interested in directly learning the data distribution p star, Instead, we indirectly learn it with the help of some latent variable z, which adheres to a known probability distribution pz, which is usually a Gaussian or normal distribution. So for this reason, we'll call pz our noise distribution. So the idea here is that since our latent distribution pz is definitely a probability distribution, which is normalized and everything, we can implicitly learn our target distribution p star by mapping points in latent space to points in data space, such that our noise distribution in latent space maps onto our target distribution in data space. But of course, the big challenge is to ensure that our mapping actually produces points from p star, and that's where the GAN comes in. So how does a GAN work? Well, basically, as we've mentioned, we have two models, a generator model G and a discriminator model D, both typically built as deep neural networks. Our generator maps our noise distribution in latent space to some generated distribution in data space, PG, which we want to align as closely as possible with our target distribution P star. In other words, we want our generated samples to be indistinguishable from our real samples. Meanwhile, it's the job of the discriminator to distinguish or discriminate between those two classes, which are the real and generated inputs. So our discriminator, model D, takes as input our data variable x and outputs a single scalar d of x, which we treat as the discriminator's prediction of the probability that x is real rather than generated. Now in practice, we limit the range of the discriminator output to somewhere between 0 and 1, and treat this as a standard binary classification problem. And again, we can choose any arbitrary neural network architecture that does the job. So on the surface, the training procedure of the GAN is actually pretty simple. The discriminator performs some binary classification task between real and generated samples, and the discriminator is trained to improve its own performance, while the generator is trained to worsen it. However, the magic of the GAN is that this seemingly very simple training dynamic can in fact push the generator to eventually create realistic-looking samples. To understand how this is possible, let's first take a closer look at the exact form of the loss function used to train our GAN, then see how it promotes the alignment of our generator distribution with our target distribution. So at the core of everything is our binary classification task. The discriminator output is the probability of our sample being real, so if our sample actually is real, then the ground truth output is 1, and if it's generated, then the ground truth output is 0. So in essence, both the discriminator output and the ground truth can be described as categorical distributions with only two categories, real and generated, and this is also known as a Bernoulli distribution. So now the goal of the discriminator is to align these distributions using some appropriate loss function. So let's derive it. So to start off with, the discriminator output d of x can be used to define a conditional Bernoulli distribution over our class labels y. Similarly, we have a ground truth conditional p star b, b for Bernoulli, and this just assigns the class label. So if x is real, then y equals 1 has a probability of 1, and if x is generated, then y equals 0 has a probability of 1. Now, if we want to align these two distributions as closely as possible, we need a measure of closeness between the distributions, and for this we use the Kullback-Leibler divergence, or KL divergence, between our two distributions. Now, this divergence can be thought of as a measure of the distance between two distributions. That being said, it's not actually symmetric, so in a way, analogies with distance are a bit misleading. But technically speaking, the KL divergence of P star B from D is the relative entropy of the distribution P star B if we assume that the distribution D is true, and this is just calculated by an expected difference of logs over P star B. So this is just the general definition of the Kullback-Leibler divergence. And now if we want to calculate this expectation over discrete variables, we can just use the following summation. Now, since we just have a log of a fraction here, we can actually split this summation like so. Now, the neat thing is that our left-hand term is actually constant with respect to d, so we can just ignore it in our training objective, which just becomes this. And of course, you may recognize this as just the cross entropy between P star B and D. Now, moving on, our situation is actually made even more simple by the fact that we only have two classes, or only two values of y, which are 0 and 1. So our loss just reduces to these two terms. Now, since all our distributions are Bernoulli distributions, and since our D distribution just looks like this, we can actually re-express our loss like so, which again we may recognize as the classic form of the binary cross-entropy loss. So our loss is just a binary cross-entropy. Now to actually train our discriminator, we just run it on a classification task using a mixed dataset of real and generated samples. The discriminator's job now is to distinguish between these real and generated samples. So intuitively speaking, it has to detect those features of the input that give away the fact that something is not real. Therefore, our final discriminator loss, L of D, is just the sum of the expected values of our binary cross-entropy term over both the real and generated distributions. Now, if x comes from P star, then P star B of 1 becomes 1. And if x comes from PG, then P star B of 1 becomes 0. So we can simplify it to just this. And of course, we can rewrite this again in terms of our noise distribution, P of z. So here we have our final discriminator loss. Now, the only thing we're missing is our generator loss. Now, of course, the ultimate objective is to align P of g with P star, but it turns out we can achieve this by using the intermediate objective of reducing the discriminator's performance as much as possible. So the generator loss is the negative of the discriminator loss, just ignoring the first term, since the generator can't actually influence this. So basically what we have here is a situation where the generator and discriminator are being trained on directly contradictory objectives. Now, in game theory speak, we can think of this expression as some value function v that our generator is trying to minimize and our discriminator is trying to maximize. So training can be framed as a two-player zero-sum game, or a minimax game, played by the generator and discriminator. Now, this just means that they're involved in a competitive scenario where each player's payoff is the opposite of the other player's payoff, and where they each seek to maximize their own payoff under the constraint that their opponent is seeking to do the same. So the minimax framework applies here because the generator is trying to minimize the value function, whilst the discriminator is trying to maximize it. Now, as it turns out, this simple game theoretic framework is sufficient to push our generator distribution to the target distribution, given that our models are sufficiently powerful and that we allow for sufficient training time. Now, this is actually quite a remarkable result, so we'll spend the next few minutes proving it. To start off, we recognize that training our GAN is equivalent to finding a Nash equilibrium of our game. This is when neither the generator nor the discriminator can decrease its loss by changing its parameters, assuming that the other model keeps its parameters constant. Now, this is an equilibrium because it means that our model parameters are stable. So let's see what it takes to achieve this equilibrium. Our strategy will be as follows. First, we're going to find an expression for the optimal discriminator given any particular generator, and we're going to call this D star. So in other words, given some generator G, this is the ideal configuration for D that minimizes the discriminator loss. Second, we're going to find the optimal generator, assuming that our discriminator remains optimal throughout the entire process. Now remember that our goal is to prove that if we train both our models to optimality, then PG is going to align with P star. Okay, so in order to find our optimal discriminator, let's start by taking our value function and expanding out the expectations to integrals. And of course, we could just rewrite this as one big integral over x. Now, if we're the discriminator, we want to find some optimal dx such that we maximize this entire integral. One way we can do that is to actually just maximize the expression inside the integral, which turns out to be valid in our situation, and this is quite feasible to do. So as a first step to find the maximum, we just take the derivative of this expression with respect to d of x, and here we're just treating p star and pg as constants. Then once we have our result, we can equate it to 0 to find a stationary point. And if we work through the algebra, we'll find that the stationary point looks like this. And it turns out that the second derivative here is also negative, so we know that it's a maximum point, which is therefore an expression for our optimal discriminator d star, given any generator g. So now that we have our first result, let's find our optimal generator given our optimal discriminator. So here we assume that our discriminator remains optimal as the generator also optimizes. Now, given that our discriminator remains optimal, our value function basically just boils down to a function of just our generator, which we call our generator criterion C. Now, to get this, we just substitute our expression for d star of g into our value function, which just gives us this. Now, as the generator, we're interested in minimizing this criterion. The first step is to realize, through some clever working, that what we actually have here is the sum of two KL divergences, where we recall the definition of KL divergence as the expected difference of logs. Now, being the savvy statisticians we are, we can also recognize this as 2 times what's called the Jensen-Shannon divergence between P star and PG, where this divergence is just half the sum of KL divergences with some reference distribution M. Now this is quite neat because we've just shown that optimizing the generator, assuming an optimal discriminator, is just equivalent to minimizing the Jensen-Shannon divergence between our two distributions P star and PG. Now this divergence is non-negative, so it has a minimum value of 0, and it reaches this value precisely and only when P star and PG are equal. So we've effectively shown that minimizing the generator loss is equivalent to our lining our target and generator distributions, at which point the criterion function becomes minus log 4. So our theoretical analysis has shown why our GAN system should optimize to a Nash equilibrium, with PG aligning with P star. However, of course, the real world is quite a bit messier, and both our generator and discriminator are real neural networks with non-infinite expressibility. So when optimizing in parameter space, we may fall into local minima, and other issues may also prevent us from reaching and stabilizing a global optimum. So it turns out that in the real world, training a GAN is not so straightforward. So on that note, let's first take a look at what should be happening as we train our GAN, then focus on some of the potential pitfalls that might plague our training. So imagine that we have a one-dimensional X. Now in the initial stage of our analysis, we have our generator and discriminator, and they're both kind of near convergence, so PG is not so far off from P star, and D is not so far off from D star, but they haven't reached them yet. Now in the second stage, our discriminator reaches convergence, so D equals D star of G. But our generator hasn't converged yet. So here we're making the assumption that the discriminator reaches convergence more quickly than the generator, which also happens to align with the analysis we showed earlier. Now, in the second stage, our discriminator converges, so it has a high discriminative capacity, and thus becomes useful to the generator in guiding it towards P star, which is the third stage. Then, finally, in the fourth stage, P of G becomes P star, and our discriminator output becomes 1/2 everywhere. So in a perfect world, this is what should happen during GAN training, and we should eventually reach convergence, or the Nash equilibrium of our minimax game, with our discriminator being completely confused between real and generated samples. But of course, the real world is not so simple. So now we're going to look at 3 potential training issues that can upset this nice story: the optimal and lousy discriminator problem, the possibility of non-convergence, and the possibility of mode collapse. So first of all, why might an optimal discriminator be problematic, especially as we've just used it to show that it can help the generator reach convergence? Well, it turns out that during GAN training, as our discriminator approaches its optimal state, the gradients of our generator parameters theta begin to vanish. In other words, as the discriminator gets too good, it can no longer transmit useful information to the generator. You can actually derive this result through some mathematical analysis, which I won't show here, but I'll link the relevant paper in the description below. Now, this is certainly a big problem because having an optimal discriminator is what guarantees that our generator loss is close to the Jensen-Shannon divergence. Yet, if our discriminator really is optimal in the real world, then our model as a whole can remain stuck due to this problem of vanishing gradients. Now, to sidestep this issue, the original authors suggest using a modified generator loss function, but it turns out that if we modify it like so, then we'll face the problem of highly unstable gradients. So in other words, whatever our choice, GAN training is difficult. Now, somewhat related to this is what we can call the problem of the lousy discriminator, where the generator updates too quickly for our discriminator to keep up. And as a consequence, the discriminator, again, cannot transmit useful information to the generator, because now it's too confused. The problem here is that if the discriminator is junk, then the generator, which relies on it, will also start producing junk, and our GAN never stabilizes to a good state. So essentially, we need to regulate our discriminator such that it's good, but not too good. And in practice, this can be achieved in several ways. For example, in GAN training, it's quite common to alternate between discriminator and generator training steps, and to allow for the discriminator to take k steps for every one step that the generator takes, where k is a hyperparameter. Another thing we could also do is set the learning rate for the discriminator parameters to be higher than that for the generator parameters. So, using methods like these, we can actually control the degree to which the discriminator reaches optimality. Now, yet another problem we have to worry about is the possibility of non-convergence. As we've seen, this can happen if we have a lousy discriminator, but it can also happen as a general feature of our training situation. And this is because not all minimax games necessarily converge. To imagine how this can happen, consider the following hypothetical scenario. We have only two model parameters, x and y. We also have two players, so player A minimizes the loss function xy with respect to x, and player B minimizes the loss function minus xy with respect to y. Therefore, the gradient of parameter x will be y, and the gradient of parameter y will be minus x. Now we can see that there's an equilibrium at the point x equals y equals 0, but it's also possible that our parameters may never converge to the solution if we alternate between optimizing A and B. For example, if we find ourselves anywhere on this box, then we're just going to trace the outline of the box in perpetuity, following a stable orbit instead of ever converging to an equilibrium point. So, in a nutshell, this is the problem of non-convergence. Now, a third notorious problem with GANs is when the generator actually learns to achieve good performance by just mapping every noise vector to the same point in data space. So, even if the generator succeeds in producing realistic outputs, it has clearly failed in the overarching goal of approximating our data distribution. However, a generator may very well come to rely on this strategy as a way of confusing the discriminator and reducing its own loss, just by producing the same output every time, which it knows to be a pretty good bet. Now, this is a common problem in GANs, and it's usually referred to as mode collapse, because in generative modeling, we're trying to capture the modes of a target distribution, but in this case, we're capturing just one of these modes. Now, one way of interpreting what's happening is this. So imagine that over the space of our data x is a landscape of values d of x that determine the discriminator's prediction. Now, if you have some generator outputs in a batch sufficiently close to each other, then our generator gradient updates may push these points to the same point, which the discriminator deems as highly realistic. Now, of course, the discriminator can then adapt and realize that these points are generated, which we can visualize as a shifting of the contour map. But then, when the generated points move due to the gradient update, they all move together. And so what we have is a cluster of generated points that will continue to all look the same. Now, mode collapse is a notorious issue in GAN training, but thankfully, over the years, people have created several solutions to address this. One such technique is called mini-batch discrimination, which, without going into the details, basically gives the discriminator information about every sample in a batch as it evaluates each individual sample. This way, the discriminator can learn to detect that points are being generated when they all happen to be very close to one another, and so this reduces the effectiveness of the strategy of just producing one output, even if it is highly realistic. Yet another approach is the Wasserstein GAN, which is an alternative GAN framework introduced to address problems such as mode collapse and training instability. But that's beyond the scope of this video. So here are a few common failure modes, and as we've seen, they can be very difficult to address because they are, in a sense, emergent outcomes of a stochastic training process. And they show that while the GAN framework is simple on the surface, actually training a GAN is anything but simple. So this is probably a good place to end our introduction of GANs. To sum up, these models use an elegant adversarial framework to achieve impressive results in generative modeling, but as we've seen, they can also be tricky to train.